Mars has 10% of the mass of the Earth. It's about half as big. Has a surface gravity of about 40% of the Earth. The mean distance from the Sun is 1.5 AU, and an AU, of course, is the distance between the Earth and the Sun. And that means it has a mean solar constant of 43% of the Earth. So it's 1 over r squared. So it's the solar constant divided by the radius squared. And it turns out that Mars has the second most eccentric orbit in the solar system. And by saying second most, I'm throwing away Pluto, I'm sorry. Mercury has the most eccentric orbit. Mars has the second most. And it's enough so that the solar constant at Mars varies by quite a bit, 36% to 52%. And that's actually pretty significant. And the tilt of the axis is such that the northern hemisphere is in the at the closest to the Sun, what we call periapsis. The northern hemisphere is tilted towards the Sun. And at apoapsis, the farthest distance from the Sun, the southern hemisphere is tilted towards the Sun. So the summers are not fair on Mars. The northern summer is much warmer than the southern summer. So the length of the day is 24.6 hours. That should seem kind of familiar. The length of our day. And the obliquity is 25%. Earth is 23 and maybe 23.5 degrees for the Earth's obliquity. The present day atmosphere, the surface pressure, average surface pressure is about 6 millibar, 6 1,000ths of a bar, where a bar is what we're standing in right now, or sitting in right now. On Mars, it was not known whether Mars had its own dynamo or not. The spacecraft had not gotten close enough to it until Mars Global Surveyor, with a very sensitive magnetometer on board, got very close to the surface of Mars, within 100 kilometers about, and made this map. And so this is basically, remember I explained how the laser altimeter built up maps by making spots. So the magnetometer flew on the same orbit and built up maps of the magnetic field after over many, many orbits as the orbit moved around the whole surface of the planet. And so these are the magnetic fields that it measured, and this is from orbit. Oops, there it is. The peak fields here are a couple of hundred nanotesla, so that's a very low, very weak field compared to what's in this room. This is we're sitting at about 50,000 nanotesla, and this is about a couple of hundred. So, but this is at 150 kilometers altitude. So if you were to go down towards the surface where the field gets stronger as you go down, you would easily be standing in a Gauss, a field similar to the field in this room. And you see how complicated it is. All the reds mean that the field's pointed, the magnetic field's pointed out of the surface, and all of the blues are the field points down into the surface. And so the magnetic fields, there are no open field lines. I don't know if you've done a one of those iron filings on top of a bar magnet, you see they form these closed loops. And so you can imagine that there are closed loops coming out of the surface from here and then looping around and going back into the surface right above it. And it forms these sort of long, elongated series of loops. And this is thousands of kilometers long. So this is very, very large scale magnetic fields. And so why do I call these fossils? And the reason I call them fossils is because these magnetic fields are embedded in the rock that are caused by magnetized rocks, magnetized crustal rocks. And how do they get magnetized? And in order to get magnetized to the levels that you see here, it had to have been magnetized in an early Mars dynamo. So what this tells us is that, the story these fossils are telling us, is that Mars once had a global dynamo field like the Earth's, similar in strength to the Earth's, and it died away.